Okay, so the ground beneath software engineering, it feels like it's really shifting, like dramatically.
Yeah, it's less a gentle slope and more a seismic event, wouldn't you say?
Totally. And the driver seems obvious, right? Generative AI, it's just exploded.
Absolutely. I mean, think about the numbers. In 2023 alone, what was it, 149 new foundation models?
Yeah, staggering. More than double the year before.
Hmm.
That's intense velocity.
Exactly. And that kind of speed, it isn't just, a flash in the pan trend. It's fundamentally reshaping the actual craft of building software.
Right. So engineers, especially senior ones, they need to adapt to become, what's the term the guide uses?
AI native engineer, that's the term. And it really captures this shift. It's about thinking and building differently from the ground up.
Okay, AI native engineer. And this guide we're using today, it's aimed right at those senior engineers trying to navigate this. Yeah.
Precisely. It's designed to be a practical resource for engineers facing this disruption.
So that's our source material for this deep dive.
Right. And our mission today really is to kind of unpack the core of that guide for you. We want to cut through the hype and focus on what actually matters.
Like the key technologies you need to get your head around.
Yeah, the tech, but also the mindset shifts. They're just as crucial. And then the practical ways to actually build things in this new era.
Because it's not just about staying employed, is it? The guide talks about huge opportunities, trillions in economic value.
Trillions, exactly. Gen AI is unlocking entirely new possibilities for what software can even do. So it's about seizing those opportunities too.
Okay. So what's the journey look like for today's deep dive?
Well, we'll start with the new toolkit, the essential tech. Then we'll explore that mindset shift, how your thinking needs to evolve. After that, we'll get into the practical blueprints for building AI applications.
And weave in some insights from pioneers in the field along the way.
Definitely. We'll bring in perspectives from people really shaping this space. Look, it's a challenging path, no doubt, but understanding this stuff puts you right at the forefront in a position to actually shape what comes next.
All right, let's do it. Let's dive in. Act 1, decoding the GenAI toolkit. What are the essential tools for this AI native engineer?
Okay, so at the very heart of it all, as the guide explains it, are the engines. These are the foundation models.
Foundation models.
Right.
What makes them foundational? What's the core idea?
Think of them as these enormous pre-trained neural networks. They have learned from just massive, massive data sets. Could be text, code, images, you name it.
So incredibly general purpose.
That's the key. Their power is in their scale and their adaptability. Unlike older AI models that were built for one specific task, you could take a single foundation model and fine-tune it or prompt it for a whole range of different jobs.
Without starting from zero every time.
Exactly. You leverage that huge initial training.
Yeah.
And they're generative because they don't just recognize patterns. They can actually create new content, text, images, code based on what they learned.
Okay, so creating new stuff. And we see this with things like large language models, LLMs, like Claude 2, Llama 2, great for text, coding.
Precisely. And then you have diffusion models like Stable Diffusion doing amazing things generating images from text prompts.
And underlying a lot of this, especially for language, is the transformer architecture.
That's the breakthrough tech, yeah. Transformers are incredibly good at understanding context and relationships in sequences, like words in a sentence. They use attention mechanism to sort of weigh the importance of different input parts simultaneously.
Right. And the scale we're talking about, it's mind-boggling, like GPT-3.
Yeah, trained on something close to 1 trillion words. And the hardware needed, the guide mentions needing infrastructure like 10,000 high-end NVIDIA GPUs. That's why they're large models. It takes immense resources.
Wow. Okay, so that scale is just,
Yeah.
yeah, hard to grasp. So those are the engines. But as an engineer, day to day, I'm probably not training those monsters from scratch, right?
Typically not, no.
So what's the tech stack I actually use to build with these foundation models?
Right, that's the AI native's essential stack. And it starts, maybe at the lower level, with the core deep learning libraries. These give you more direct control if you need it.
Things like TensorFlow and PyTorch.
Exactly. They're the open source giants. TensorFlow is often seen as really strong for production deployment, very robust ecosystem. PyTorch is incredibly popular in research, known for its flexibility, its sort of Pythonic feel.
Do I need to be an expert in these day one?
Not necessarily an expert to start, especially if you're using higher level tools, but understanding the basics of how they work. Invaluable, especially for speeding, customizing, or when you need to go beyond simple API calls. Think of them like the SDKs or even the operating system layer for this AI world.
Got it. The foundational OS layer. Okay, what builds on top of that? How do we make using these models easier?
Well, that's where you get into ecosystems, designed to abstract away some of that low-level complexity. And a huge one here is Hugging Face.
Hugging Face. Yeah, they seem to be everywhere now, kind of like the GitHub for AI models.
That's a perfect analogy. They've really democratized access to state-of-the-art AI. Their Transformers library, for instance, gives you a super easy way to download, use, and even fine-tune thousands of different models for text, speech, code.
And they have something similar for images too, right?
Yep, their diffusers library does the same for generating images, audio, multimedia content. And then there's the Model Hub itself.
The Hub, that's the library card catalog.
Pretty much. Over 120,000 pre-trained models last I checked. You can just browse, find a model suitable for your task, pull it down, and start experimenting almost immediately.
Yeah.
It massively lowers the barrier to entry.
Okay, so engines, foundation models, core libraries, TensorFlow, PyTorch, and then easy access and abstraction with Hugging Face. But how do you make these models do complex, multi-step tasks? Or connect them to my company's specific data?
Ah, right. That's where you need orchestration. Raw models are powerful, but often isolated. They need to interact with the real-world external APIs, databases, follow specific workflows.
And this is where tools like LangChain come in.
Exactly. LangChain is really focused on building sophisticated applications by connecting LLMs together and with other components.
So chaining calls?
Shading calls, yes, but also connecting them to external data sources, giving them access to tools like web search or calculators, managing conversation history or memory, creating agents that can reason and act. It helps structure complex LLM-powered workflows.
Okay, so LangChain for building complex apps. What about Lemma Index? It sounds similar but different.
Lemma Index has a more specific focus, primarily on connecting LLMs to your data, whether it's private documents, databases, APIs.
So less about complex chains, more about the data connection.
Right. It provides tools to ingest data from various sources, structure it often by creating vector embeddings, and then index it so the LLM can efficiently query and retrieve relevant information from that data.
And that's key for RG, Retrieval Augmented Generation.
Absolutely critical for ARG. We hear that acronym constantly now, and for good reason.
Explain RG simply. What's the core benefit?
Okay, so instead of the LLM just relying on its internal, potentially outdated training data, RG first retrieves relevant pieces of information from an external knowledge source, like your company's documentation, stored in a special database.
And then
it feeds that retrieved information to the LLM as context, right along with the user's original question. The LLM uses this fresh, specific context to generate its answer.
So it makes the answers more factual, more up-to-date, and specific to my domain, and reduces hallucinations.
Precisely. It grounds the LLM's response in external reality, making it much more reliable for tasks requiring factual accuracy or domain-specific knowledge. And this brings us neatly to the crucial, often unseen, piece of infrastructure enabling RG.
Ah, the vector databases.
The unsung heroes, exactly. These are specialized databases built to handle vector embeddings.
Embeddings. Those are the numerical representations of data, right? Like turning text into a list of numbers.
You got it. High-dimensional lists of numbers that capture the semantic meaning. Vector databases are optimized to store these embeddings and perform incredibly fast similarity searches.
So you turn the user's query into a vector too and find the closest matching vectors in the database.
That's the core idea. Find the data chunks whose vector representations are closest, meaning they're semantically similar. This is lightning fast and way more powerful than old keyword search.
And vital for ARG, obviously.
Vital for AG, but also increasingly used for recommendation systems, anomaly detection, image search. Anywhere, understanding meaning and context is key. The guide mentioned Forrester predicting a 200% jump in adoption just this year. That tells you how central they're becoming.
Okay, let's recap the stack. Foundation models, engines, TensorFlow, PyTorch, low level, Hugging Face, excess abstraction, LangChain lemma index, orchestration data connection, and vector databases, semantic search RAG backbone. That's quite a tool set.
It really is.
Yeah.
And the guide makes a key point here. While getting started, maybe hitting an API or using a Hugging Face model, is getting easier.
Yeah.
Achieving production-grade reliability with these tools, that's a whole other level of challenge.
Why is that?
Because you're dealing with probabilities, not certainties. Models can hallucinate. They can be sensitive to prompts. You might need careful fine-tuning, robust data pipelines, monitoring for drift. It adds layers of complexity that traditional software maybe didn't have in the same way.
So engineers might specialize in parts of this stack.
Oh, absolutely. You'll see specialists in prompting and data engineering for AI and LO apps, but the guide stresses that having that holistic view, understanding how all these pieces fit together and interact, is really crucial for anyone wanting to build robust, reliable AI systems.
Makes sense. You need to understand the nature of the beast, not just the individual clothes. Which leads us perfectly into Act 2, the metamorphosis, cultivating the AI native mindset. This isn't about tools anymore, it's about how you think.
Exactly. It's a fundamental shift in perspective. And maybe the biggest one is moving from deterministic to probabilistic thinking.
Okay, unpack that. Deterministic. That's normal code, right? Input A reliably gives you output B, assuming no bugs.
Right. You write explicit instructions, if this, then that, and the computer follows them precisely. Predictable. Verifiable in a straightforward way.
But AI isn't like that, especially generative AI.
Not fundamentally.
Huh.
It's probabilistic. It generates outputs based on patterns and probabilities learned from data, not by executing explicit step-by-step logic in the same way.
Meaning, the same input might not always produce the exact same output.
Precisely. There's inherent randomness, variability, uncertainty, and that changes everything about how you design and test.
So you can't just write a test that says assert output equals expected output.
Often, no. You need to think statistically. You need to design systems that can handle a range of possible outputs that can manage ambiguity gracefully. How does it fail well when the AI gives a weird or unhelpful response?
So testing becomes more about statistical metrics, confidence scores, evaluating the quality of the output range rather than a single right answer.
Exactly. You're looking at things like BLEU scores for translation, Archie for summaries, or maybe defining custom metrics. And you need much more robust error handling and fallback mechanisms built around this uncertainty. It's a different way of building for resilience.
That's a huge mental shift. And it feels very tied to the next point, the data-centric revolution.
Absolutely intertwined. In traditional software, you write the logic, the code, and data flows through it. In the AI world, particularly deep learning, the data, in a very real sense, becomes the code. It shapes the model's behavior directly during training and fine-tuning.
Which means that old saying, garbage in, garbage out.
It's amplified tenfold, maybe 100-fold. The guide is emphatic. Data quality is paramount. If your training data is biased, incomplete, or just plain wrong, your model will inherit those flaws.
So data pipelines aren't just background tasks anymore.
They are core infrastructure. Collecting data, cleaning it, labeling it accurately, versioning it like code, validating it. These are first-class engineering problems now. And you need continuous feedback loops.
Feedback loops.
Yeah, monitoring how the model performs in the real world, collecting user feedback, identifying where it's failing, and feeding that information back to improve the data or retrain the model. Alexander Wang from Scale AI really hammers this point. Robust data infrastructure isn't optional, it's foundational. Data engineering is moving front and center.
Okay, probabilistic thinking, data centricity, and the third big shift, maybe the most talked about new skill, prompt engineering.
Right. It's the new interface, isn't it? How we communicate our intentions to these incredibly powerful but fundamentally alien intelligences.
It's more than just asking a question, though.
Oh, much more. It's becoming an art and a science. Crafting inputs prompts very carefully to guide the LLM towards the specific kind of output, the tone, the format, the reasoning process you need. The guide highlights several advanced techniques that are becoming crucial.
Like giving the model examples in the prompt itself.
That's few-shot prompting.
Yeah.
Yeah, providing maybe 2, 3, 5 examples of input-output pairs helps the model understand the task better. Then there's chain of thought prompting, or COTI.
COTI, that's getting the model to show its work.
Kind of. You explicitly ask it to think step by step, or lay out its reasoning process before giving the final answer. And remarkably, this significantly improves performance on complex tasks like math problems or logical puzzles, especially in larger models. It seems to help them access their latent reasoning capabilities.
And people are building on that, right? Like tree of thoughts.
Exactly. That's an evolution where the model explores multiple reasoning paths, kind of like branches of a tree, evaluates them, and pursues the most promising ones. It's even more deliberate, allowing it to tackle problems that require more exploration.
Okay, what about making the LLM interact with the outside world, get real-time info, or use tools?
That's where techniques like REACT, which stands for Reason and Act, come in. The prompt guides the model to interleave its internal reasoning steps with actions, like performing a web search, using an API, looking up something in a database, or calling another tool.
So it can reason, act, observe the result, and reason again.
Precisely. It creates a loop, making the model much more powerful for tasks needing up-to-date information or interaction with external systems.
Mm-hmm.
And of course, there's RAG, which we already touched on.
Right. Retrieval augmented generation, using a vector database to fetch relevant info first.
Yeah, retrieving documents, then prompting the LM with that context.
Yeah.
Super important for factual accuracy.
Andrew Ng called prompt engineering a new kind of literacy. It really feels like that.
It absolutely does. It's how we effectively collaborate with these models. And it's moving so fast, the guide even mentions tools like Procami popping up, which try to automate the process of finding the best prompts.
Wow. Okay, but this ability for AI to generate stuff so quickly, especially code, it leads to something the guide discusses, a term from Andrej Karpathy, vibe coding.
Yes, vibe coding. It's a great term.
What exactly is it?
It's basically generating code or building features using AI prompts based more on intuition or a vibe that the output looks okay or feels right, rather than a deep, rigorous understanding of what the code does or how it integrates.
Sort of like, hey, Copilot, make this button do that, and if it looks like it works, ship it.
Kinda, yeah. Karpathy pointed out it can create this illusion of accelerated productivity, especially for quick experiments, hackathons, throwaway weekend projects, as he put it.
But I'm sensing a but coming.
A big but. The guide warns this approach leads directly to what it calls technical chaos in any real long-lived production system.
How so?
Because you end up with code that's hard to maintain, incredibly difficult to debug when something goes wrong, potentially insecure, and almost impossible to extend reliably. It lacks a coherent architecture. It's just isolated bits of magic glued together. The guide is pretty blunt. This seriously compromises the integrity of the system.
Ouch. So what's the antidote to vibe coding?
Rigor. Plain simple. And tied to that, what the guide calls epistemic humility.
Epistemic humility, meaning
Recognizing the limits of our knowledge, and crucially, the limits of the AI's understanding. The AI isn't thinking like a human. It doesn't comprehend in the way we do. It's an incredibly sophisticated pattern-matching machine.
So the engineer's job is critical oversight.
Absolutely essential. You have to systematically question, verify, and validate everything the AI produces, especially code. The focus shifts. It's not just, did it generate something that runs? It's, do I understand how this works? Why did it produce this specific code? Is it correct? Is it secure? Does it fit our architecture?
So AI-generated code needs the same code reviews, the same testing, the same CI/CD scrutiny as human code, maybe even more.
Even more, arguably, because the failure modes can be less predictable. You need that human judgment layered on top.
That feels like a really important counter-narrative to the AI will write all the code hype. The human is still crucial, but the role shifts.
It shifts significantly towards verification, integration, and architectural integrity. And in a field changing this rapidly, that rigor needs to be paired with another key mindset trait.
Let me guess. Continuous learning.
And active experimentation. The guide quotes Fei-Fei Lai saying you have to dive headfirst into an era of ongoing experimentation. It's not enough to just read blog posts.
You need to get your hands dirty.
Constantly.
Yeah.
It requires curiosity, a growth mindset, being okay with not knowing things, seeing failures as learning opportunities. It means actively following researchers, reading papers perhaps, joining communities, trying out new libraries and models as soon as they drop. It's a commitment.
And part of that is figuring out how to use AI itself to learn faster. Karpathy's cognitive offloading idea.
Yes. Strategically using AI to handle the grunt work, summarizing papers, generating boilerplate code, explaining concepts, drafting documentation, freeing up your human brain cycles for the harder stuff.
Like the high-level design, the creative problem-solving, the ethical considerations, the deep debugging.
Exactly. You offload the routine cognition to the AI, but reserve your focused mental energy for the tasks that require deep human insight, judgment, and creativity. It's a balancing act, the guide notes, between the speed AI offers and the rigor humans must provide. The AI native engineer learns to navigate that tension effectively.
Okay. Wow. So you've got the toolkit, we've got the mindset shifts, probabilistic thinking, data-centricity, prompt mastery, rigor over vibe, continuous learning. Now let's get really practical. Act 3. Engineering in the GenAI era, practical blueprints. How do we actually build stuff?
Right, the nuts and bolts. And it often starts, wisely, by adapting a classic concept, the minimum viable product, or MVP, but for AI.
An AI MVP. How's that different from a regular software MVP?
The core goal is identical.
Yeah.
Build the simplest possible version that delivers core value and lets you test your key assumptions with real users fast. De-risk the idea.
Yeah.
But the steps for an AI MVP look a bit different, according to the guide.
What's step 1?
Ruthless focus. Identify a genuine, significant problem that AI is uniquely suited to solve. Not just, let's sprinkle some AI on this. What can AI do here that wasn't possible or practical before?
Find the AI superpower for a real pain point. Makes sense. Then,
Scope it down dramatically. Focus on one single AI use case for the MVP. Don't try to boil the ocean. Maybe it's summarizing meeting notes. Maybe it's generating product descriptions for one category. Maybe it's classifying customer support tickets into just 3 types, one specific valuable feature.
keeps it manageable. What about data? Do I need terabytes of perfectly labeled data for an MVP?
That's a common fear, but no, typically not for MVP. The lean approach applies here too. Collect just enough data, but make sure it's reasonably clean and well labeled for that one use case.
How much is just enough?
It varies hugely, but the guide suggests maybe starting with the few hundred examples could be enough to get a basic model working or to fine-tune a pre-trained one for a narrow task. You might use public data sets, synthesize data, or even use Wizard of Oz techniques early on.
Wizard of Oz, where a human fakes being the AI.
Yeah, behind the curtain, a human performs the task. It's great for testing the user interface and validating if the proposed AI capability is actually useful before you build the complex AI backend. Just need to be transparent about it if interacting with real users.
Okay. And the AI model for the MVP itself? Build our own.
Almost certainly not. Leverage the giants. Use readily available pre-trained models, maybe from Hugging Face, or tap into powerful APIs from OpenAI, Anthropic, Google, Cohere. Get state-of-the-art capabilities off the shelf. Focus your effort on the application logic and user experience around the AI.
So, sharp focus on problem use case, just enough data, use existing models, APIs, and nail the user experience. Keep the architecture simple, too.
Absolutely. Start simple for the MVP deployment. Maybe Google Colab for early tinkering. Then platforms like Hugging Face Spaces, Streamlit Cloud, or basic platform as a service options on AWS, Azure, or GCP. Keep it lean.
The whole point seems to be learning and de-risking as fast as possible.
Exactly. AI projects have inherent uncertainty. Will the model actually perform well on diverse real-world user inputs? Is the data quality sufficient? Are there unexpected biases or failure modes? The MVP gets you real feedback before you sink massive resources into scaling something that might be flawed. It's about mitigating risk. As Deborah Golden from Deloitte often points out, fostering that culture of rapid experimentation is how you unlock value.
Okay, so the MVP validates the core idea, but then you need to scale it, make it robust, reliable. That's where LLMOps comes in.
That's the transition. LLMOps, large language model operations. It's the discipline of operationalizing these LLMs for production environments. It borrows heavily from MLOps, machine learning operations, but has its own unique twists.
What makes LLMOps unique or more challenging than traditional MLMs?
Well, many core principles are similar. Automation, monitoring, governance, collaboration between data science, engineering, and ops. But the specifics get trickier with LLMs.
Like what?
You still need rigorous data management, of course, but now prompt engineering and management becomes a whole new discipline within ops.
Treating prompts like code, versioning them, testing them.
Exactly. Prompts are critical configuration, maybe even code. They need CI/CD, version control, testing frameworks. Then you have specific processes for model fine-tuning and development if you're customizing models. Evaluating model performance is harder too. Metrics for generative tasks are complex.
Right. How do you measure the goodness of generated text or images consistently?
It's tough. You use things like BLEU, RUG, maybe human evaluations, track toxicity scores, bias metrics. It's multifaceted. And the model inference and serving infrastructure needs to handle potentially huge models and GPU demands.
And monitoring. I imagine that's a beast.
It's incredibly critical and complex. You're not just watching CPU usage. You're monitoring for performance drift. Is the model degrading over time? Data drift is the input data changing, concept drift. And crucially, you're monitoring for harmful outputs, bias, toxicity, hallucination rates, checking for misuse patterns.
And that feedback loop we mentioned earlier.
It's essential. Continuous monitoring has to include mechanisms for capturing human feedback on the model's outputs. Did users find this helpful? Was this answer wrong? Was it offensive? That feedback is gold, often feeding back into data curation or reinforcement. Learning from human feedback, RLHF, to improve alignment.
So unique LLMOps challenges include GPU management, complex evaluation metrics, managing prompts as code, integrating human feedback pipelines, handling potentially brittle LangChain style chains.
You've got it. It's a rapidly evolving field, But putting robust LLMOps practices in place is absolutely non-negotiable for running reliable, scalable, and governable LLM applications in production.
Mm.
It's how you move from cooled experiments to trustworthy systems, as Deborah Golden would say, scaling that innovation responsibly.
And that word responsibly leads us to the final and maybe most important blueprint: championing responsible AI.
Absolutely fundamental. This can't be an afterthought. With the power these models wield, the ethical responsibility on engineers and organizations is immense.
What are the biggest concerns the guide highlights?
Several key areas. Bias is a huge one. Models learning and amplifying societal biases present in their training data. Hallucinations models just making things up, sometimes very convincingly.
Right, stating falsehoods as facts.
Exactly. Then there's toxicity and misuse the potential for models to generate hate speech, disinformation, deepfakes, or even assist in cyber attacks. There's the fact that they lack true understanding, even when they sound fluent. And of course, major questions around intellectual property, data privacy, and consent.
It's a minefield.
Hmm.
How do engineers navigate this? Are there guiding principles?
There are. The guide points to established frameworks like the ACM Code of Ethics or the IE's Ethically Aligned Design Principles. Common threads emerge: fairness, non-discrimination, accountability, transparency, or at least explainability where possible, privacy protection, reliability, and safety, the principle of do no harm.
Okay, those are principles. But what can engineers do practically in their daily work?
The guide outlines concrete mitigation strategies. It starts with data diligence, meticulously examining, cleaning, and filtering data used for training or fine-tuning to minimize bias.
Okay, better data in. What else?
Safety-focused prompt engineering, designing prompts and system-level instructions, meta prompts, to explicitly steer the model away from harmful topics or outputs, using guardrails.
Fine-tuning for alignment.
Yes, techniques like RLHF are specifically designed to fine-tune models to be more helpful, honest, and harmless based on human preferences. Using RA, as we discussed, helps reduce hallucinations by grounding outputs in external facts.
Human oversight.
Crucial. Implementing human-in-the-loop workflows for sensitive tasks or outputs, where a person reviews or approves the AI suggestion before it goes out. And finally, rigorous testing specifically designed to uncover ethical risks, testing for bias across different demographic groups, red teaming to find ways to elicit harmful content, testing security vulnerabilities.
It sounds like a lot of extra work.
It is work, but it's essential work. When you hear warnings from pioneers like Geoffrey Hinton about existential risks, or Sam Altman talking about the need for iterative deployment and safety alongside AGI development, or Yoshua Bengio calling for global coordination on risk assessment, it underscores the stakes. Engineers are building this future, so they must build responsibility in from the start.
Ethical thinking isn't just for philosophers, it's an engineering requirement now.
Exactly. It has to be part of the daily design, build, and test cycle. It's about building systems we can genuinely trust.
Wow. Okay, what a journey. We've covered the new GenAI toolkit, those crucial mindset shifts for engineers, and the practical blueprints for building the AI MVPs, scaling with LLMOps, and the absolute necessity of responsible AI.
It's a lot to take in, definitely. It's a demanding transition, requiring constant learning and adaptation, but honestly, it's also incredibly exciting.
Yeah, it puts engineers right at the heart of this massive technological wave.
And the future it paints. It's not really about engineers being replaced, it's about augmentation. It's more like a collaboration.
A symphony between human creativity and AI capability.
I like that. Think of Karpathy's co-pilot metaphor. The human is still directing, still responsible. Or Sam Altman's idea of AI as virtual coworkers that amplify what humans can achieve. The engineer's role elevates.
To become more of an AI orchestrator.
Yeah, designing the systems, selecting and guiding the models, ensuring data quality, managing the operational complexities, and critically, safeguarding the ethical integrity. It becomes a more strategic, architect-level role, arguably.
That sounds incredibly empowering, actually. A huge opportunity.
Immense. Sam Altman has that quote. Something like, in an AI-augmented world, good ideas are the limit, not specific skills. It reframes skill itself. It's less about knowing a specific syntax.
And more about strategic thinking, problem framing, creativity, critical judgment, ethical reasoning.
Exactly. Those uniquely human capabilities become even more valuable when paired with powerful AI tools.
So if we had to boil down the call to action from this whole deep dive, what would it be?
I think it's 4 things. First, dive in. Don't wait. Start learning these tools, concepts, and models now. Second, experiment. Get hands-on, build things, break things. As Fei Fei Lai said, learning by doing is paramount.
Third.
Learn continuously.
Right.
Cultivate that AI native mindset. Embrace the uncertainty. Focus on data. Hone your prompting skills. Stay rigorous. Stay curious. It's a marathon, not a sprint.
And finally,
Shape the future responsibly. Make ethical considerations and responsible AI practices an integral part of your engineering workflow from day one. Don't bolt it on later.
dive in, experiment, learn continuously, and shape the future responsibly. That's a powerful mandate.
It is. It's an investment in yourself, your career, and frankly, in building a future technology that benefits everyone. It's about being an active participant, not just a bystander.
Absolutely. Okay, to wrap this up, let's leave our listeners with something to chew on. A final provocative thought based on everything we've discussed.
How about this? In a world where AI can generate code, perhaps faster and sometimes even better than humans for certain tasks, what becomes the most valuable, the most irreplaceable contribution you bring to the table as a software engineer? What's left when the code writes itself?